yesterday. That one did come to my email, but others haven't. I'm not sure where they are. Doesn't matter. I will definitely have a recording from one of the periods for you. So today's calendar, hopefully you can all see that. Unlike last period when I forgot to share my screen. Today's calendar starts out with a caveat. Please do your own work. We're going to finish talking about electron configurations. They won't go away. They'll come back again in chapter 7 and 8, but I want to wrap it up for this week. And then there's some exceptions to configurations we'll talk about. The work for today is on doing electron configurations that are called noble gas configurations, and I'll explain that. That'll be due Thursday before you get to class. Tomorrow, your asynchronous assignment, we won't be together, not really together, but you know what I mean. We won't be live. Is on academic integrity. This is never a fun thing to talk about, but it's really kind of getting out of hand, I feel, and so do some of the other teachers that I am aware of. People are turning in work that other people did. And that is an issue, obviously, in a online setting. It's a lot easier to do that than it is in the classroom, but it's starting to bother me quite a bit. And I caught a few people before the end of the semester, and I am
Ms. Sketches, are you muted?
Possibly.
You're not muted.
Okay. So, can you guys see my screen? The
yes.
calendar. All right, good. And you can hear me, at least most of you?
Yeah.
Okay. I'll try and speak louder. So there's been a lot of, I've caught several pairs of people in different classes with the same exact work. And I thought that the administration was going to do something, and they didn't. I gave those individuals zeros, okay? Yesterday when I was I had to go back through and look at the assignments that were due, the review assignments, and I realized there was a very obvious duplicate for a pair of people, so I gave them both zeros, and then a whole bunch of you had different elements than what I gave to 6th period. So some of you had stuff from 1st period, some people in 2nd period had stuff from 6th period. There's a lot of swapping going on. And each class period got different elements, and I know what they are, and because I made my own slides, and yeah, it was disappointing. So because I'm not sure who gave who what, how that happened exactly, I went ahead and just gave half credit to people that did the wrong elements from a different class. So I just want you to understand, so tomorrow there'll be an assignment on academic integrity. You probably understand already what it means to have integrity, but I just want to emphasize that sharing answers is not having integrity. Helping other people is fine. Guiding other people is fine, but turning in other people's work and representing it as your own is not fine. Also, a lot of you may not realize that you think you're being a good person and giving your work to somebody else. That's also not academic integrity, okay? And both taking someone else's work and claiming it as your own, or giving your work to someone else for them to use as their own, knowingly or not, it turns out, can get you in a whole bunch of hot water in college, especially. In high school, can't do detentions, slap on the wrist, you get a 0. It's not gonna probably tank your whole grade. But what it is gonna tank is your self-esteem, because you're not doing the work yourself, so you're gonna feel kind of crummy about yourself. And it's also going to make you less likely to be successful going forward. Okay, all of the stuff that we're doing builds on itself, and you need to have the starting knowledge to be able to use it going ahead. It's really doing yourself a disservice. I know you're not doing it on purpose to be bad, okay? And you're not bad people. You want to get your assignment done. You want to get those points. You want to go, go, go. But you don't want your doctor to have made it through med school by taking all of her assignments from other people and turning them in, okay? You want to know that that person actually knows this stuff. And so when you get to college, if they catch you, and that's the caveat, of course, if they catch you, you'll have to go in front of an interrogation board. Every college has a different name for it, but they'll put you in front of a group of people and they'll hammer you about why you did this, why does it look the same, why is it, and if they don't like your answer, they can kick you out for that semester, they can give you a fail for that class, they can kick you out of the university completely. Obviously, there's different degrees. You've already heard that with your English classes and your history classes about plagiarism in your writing. They have turnitin.com. It's kind of hard to use that for the sciences and math because you're all supposed to get the same answer, but you're all supposed to do it on your own. So, yeah. It doesn't do you any good, and you're not really doing your friend a favor giving them your work, okay? And you'll both get in trouble. Obviously, it's if you get caught, right? We've all probably driven over the speed limit once or twice. Have we been caught? No. But when you do get caught, then you slow down for a while. Anyway, I hope you understand my point. I can't have it for the next semester with the kind of sharing, cheating that I've seen towards the end of this last semester. So I want to help you to see why it's maybe not a good idea. And we'll have an assignment tomorrow on academic integrity. Yeah. That's it for my soap opera for today. Sorry. So the noble gas configuration stuff, each period today has had different elements except for the sample. And so if you want to ask someone in first period about you didn't catch it, you don't understand it, that's fine. But do your own stuff. And it doesn't help you to get the answer. Ask me, email me, message me. I will try to get to you, I promise, okay? Promise, promise, promise. All right, enough of that. So what are we doing today? Well, I would like you to please kindly get out paper and pencil, or pen if you prefer, and jot down notes as we go along. It's more likely to stick in your brain if you do, I promise, okay? The first thing I want to show you is this interactive. I was going to do an assignment with this website, but I'll just show you and then that'll be the end of it. And if you want to go back and play with it, I'll put the link in today's recording. But let's just look at this really quick. This is from learner.org. It's a, they're affiliated with NOVA and PBS. So this is how to build an atom. And what it does, I hope this stuff down at the bottom looks familiar. These are the orbitals. You notice there's a 1s, a 2s, a 3s. They're just the same shape, just bigger as the number gets bigger. Same with the 2p and the 3p. And then there's a square for helium from the periodic table. Electrons, here's a filling diagram. And you'll notice as I go along that it will change. All right, so let's just run through this really quick. So the first element is helium, element 2. And so you should hopefully know that helium's up here at the top of group 18, the noble gases. And helium is at the first period. It's at the end of it. So even though it's on the P block side of the table, it's really an S block element. Okay? So hydrogen and helium only have a 1s orbital. And since s orbitals only get 2 electrons, having 2 electrons, it's full. Okay? So I'm going to pull up the 1s. I'm going to pull in an electron. Notice it's just bopping around in there randomly. It is not going in a path. Notice that in the filling diagram, there's an up arrow and a down arrow to indicate the plus minus 1/2. That orbital is now full. The 1s is full. So I think we're done. 2 electrons, 2 protons. We should be done. Yay. Okay. Next element is carbon. Carbon is element 6. That means there's 6 protons. What line is carbon on? It's on the second line, the second period. What block is carbon in? It's in the P block. And it's in the second column of the P block. So that means it's 1s has 2 electrons, it's 2s has 2 electrons, and it's 2p has 2. So 1s, just like we did with helium, drag up an electron. Boop. Boop. Okay, full. Aufbau says I can go up to the next layer now. The next layer is the 2s. Maybe. Notice same shape, just a little bit bigger. It also can have 2 electrons. I may be losing my kinetic. Whoop. There we go. Let's see what happens. Boop. All right. So 1s2, 2s2. Next thing are the p's at the second energy level. Getting something wrong here. Sorry. px, py, pz, and it's going to tell me that I don't need all 3 of them for this particular element. That's fine. I'll take one away. Boop. Oh, it doesn't want to let me take it away. I may have to reset. And there we go. Oh my goodness. Oh my goodness. Okay.
You might be able to press undo.
That would be a good thing, but that is not working either. So we're just going to see what happens. We're going to put 1 in here, and we're going to put 1 in one of these. Yay! Well, it's not exactly right, but it's close enough. There's 2 and 2 and 2. Let's see if it works. I haven't done that. Yay! So 6 electrons spread out. Remember, seats on the bus, you can't load 2 electrons in the same one, and I'll try and show you that with sodium. So again, oops. Sodium's here on the 3rd line. Hydrogen's 1, lithium's 2, sodium's 3. It's in the S block. It has 1 electron in the S block. 3s. But the 1s has to fill, so we need 2 in there. The 2s is the next layer. We get 2 in there. Now I know I need all 3 of the 2p's because they have to fill. Okay. And remember, you have to put them in different orbitals. If I try and put it in here, it's going to say, no, you can't do that. Every p orbital needs at least 1 before doubling up, before getting a second one. Remember, that's Kunz rule, the seats on the bus rule. So I'm going to put it here, and here. So notice we're all half full. Okay. And then we're going to get another one. Let's see what if it likes this or not. Another one. And another one. Yay! All right. 2 and 2 is 4. 3 times 2 is 6. 4 and 6 is 10. I need 1 more. That means I need another cloud. So the 3s gets 1 electron. 10 and 1 is 11. Let's see if we got it. And of course we did. Okay, so I just want to show you that, and I again will put the link if you want to play around with it and try argon on your own. You can, not necessary, but kind of, I don't know. I think it was fun. All right, it's probably more fun because I get to do it and you just have to watch, but that's okay. All right, so what are we talking about today? We're talking about the elements called the noble gases. Noble gases live in group 18. Back in the old days, they had a different number and letter thing with them. I'll talk about that in a minute. But they are elements that don't react. Okay, they don't intermingle with the other elements. They don't make compounds. They exist on their own in pure form. So like nobility couldn't be bothered to associate with the peasants, right? It turns out the reason why they're non-reactive is their s and p orbitals for that energy level, that layer that they're on, are full. Now, of course, helium is a noble gas, but it doesn't have any p orbitals. So there's always like these little exceptions to everything in chemistry. It's really annoying, but the s orbital is full for helium. After that, second, third, fourth, fifth, sixth, seventh line, they're all so full. I'm going to come back to this tons more in the future, but 2 in the S, 6 in the P makes 8. That's called an octet. Those are your valence electrons. It's the valence electrons, the outermost electrons, that bump into the outermost electrons of other atoms and form bonds to make compounds. Some elements lose electrons, some elements gain them. They're all in those bonding processes, and it's all to achieve their octet. There's a lower energy level when they're all filled. It's balanced, it's symmetrical. All right, so that's it, our quick and dirty introduction to noble gases. We'll get into them more on Friday, hopefully. So noble gas configuration notation is a shorthand notation that we use. Instead of all this 1s2, 2s2, 2p6, 3s2, 3p6, all that stuff, we use the noble gas configuration notation, okay, to minimize waste in pencil lead. So the first thing you need to know to do this properly is where your element is, what period it's on. For the work we're doing right now, you look for the closest noble gas, it's going to be on the previous line. So remember, you're reading the periodic table left to right. It's going to be on the line above your elements line on the far right, group 18. You're going to take the symbol for that element, He for helium, Ne for neon, Ar for argon, and put it in square brackets. And then whatever your element has in addition for electrons, you add that in, and I'll show you. Okay. So here's helium. Here, 1s2. Here's neon, ends with 2s2, 2p6. 3s2, 3p6. There's 4s2, 3d10, 4p6. Right? Helium ends line 1. Lithium's the next element on line 2. Helium has 2 electrons. Lithium has 1 more. Carbon is also on line 2. It's got 1, 2, 3, 4 more electrons than helium. Neon ends this period with 10. Sodium has 1 more electron than neon. Okay? So it's the same as neon plus 3s1. Okay, so let's look at this together really quick. Here's helium. Here's how we learn to do electron configuration. 1s with 2 electrons, 1s2. For our purposes, for noble gas configuration, if I ask you for the noble gas configuration for helium, you just put the symbol in the brackets and store it. Okay? Lithium, again, is just like helium, except it's got this 1 more electron. Normally, we'd write it 1s2, 2s1. We can write it He in brackets 2s1. It's the same thing as helium plus 2s1. Now, it doesn't save you that much energy, honestly, for the second period to be putting helium in brackets. It really doesn't help that much. But you'll see when we get to sodium, it's a big help. All right, carbon also has its 1s filled, but it also has the 2s filled and 2 in the 2p. Normally, we'd write 1s2, 2s2, 2p2. But we can also put helium in brackets and put 2s2, 2p2. So it has what helium has, plus it has these other 4 electrons. Okay, neon is the end, the next noble gas. This is its configuration. 10 electrons, 2 in the 1s, 2 in the 2s, 6 in the 2p. It's a lot easier if we just write neon in square brackets. Just I got one thing out of order, sorry. Sodium is just like neon, plus one more thing. So what we can do is write neon in brackets, 3s1. That's a lot shorter than this. So once you get the hang of it, it's really a lot easier to do noble gas configuration, but you still have to know this other stuff. Okay. Some electron configurations are exceptions to our rule. So remember the Ochbau principle says you got to fill the lowest energy first before you go to a higher energy. You might recall that on the 4th period, we've got 4s, and then it goes 3d. I tried to explain to you that those 5d orbitals have 10 maximum electrons. It takes more energy to hold them together. And so that 4s and the 3d, they're really close in energy. So remember, the electron orbitals overlap, like you just saw on that little interactive. And the electrons aren't in a fixed path, so they can slide a little bit. And that's where the transition metals kind of mess people up for a long time. So let me go back to this. There it is. Sorry, I couldn't find my stylus. I think I plugged in. Am I plugged in? There we go. I've told you already, these are the S block elements. Back in the old days, so this is group 1, group 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 18, so noble gases. Well, back in the old days, they used Roman numerals for everything, right? This used to be called 1A, this used to be 2A, 3A, 4A, 5A, 6A, 7A, and then the noble gases were group 8A. These are what we call the representative elements. They best represent a repeating pattern or periodicity, and we'll talk more about that in chapter 6. Every element in this family combines in the same way with elements from this family, or elements from this family, or elements from this family, a repeating pattern. Every element in this column combines the same way with these, and these, etc. So it was a beautiful thing. They tried originally to group the elements into 8 groups. And there was actually a man that made a big presentation to the Royal Society about how, oh, there must be 8 groups of elements because there's 8 notes in an octave. Chemistry and music, they're just alike. They're not. So that's okay. He was warned. He was onto something. There's a whole bunch of other elements that don't follow the pattern. Why? Well, it turns out it has to do with these d orbitals. Okay, so remember the d's. There's 5 of them. The d's is with the donuts. Okay, the s's have 1. The p's have slanty freeze. Okay, so we're just focused right in here. This group of elements right here is zinc, copper, nickel, cobalt, iron, vanadium, titanium, super important, quote unquote, real metals. Okay, they're a big deal. Okay, you get down into silver and gold, obviously they're important too, but most of the metals that you're familiar with live here. Okay? And so they're doing some weird stuff with their d orbitals. It turns out, again, because the s is just a little bit lower than the d's, I'm not doing it very well, sometimes the s orbital electron can slip up in energy, if you will. So what does that have to do with copper? So the example in your book is about copper. So if I look at copper, I know it's in the d block, and it's in the 1, 2, 3, 4, 5, 6, 7, 8, 9th column of the d block. Every element in this group ends with D9. okay? In a d orbital, there's 9 electrons. Every element in this group has S2, whether it's 4s2, 5s2, 6s2, doesn't matter, okay? Silver ends with 4d9. Remember, these are offset. This is the 3ds, this is the 4ds. What does that have to do with anything? Well, it turns out if the 4s is full, that's great. That's off bow, fill the lowest first. And then we do 1, 2, 3, 4, 5, 6, 7, 8, 9. This 1d orbital is half full. That makes it, the best explanation is it makes it unsymmetrical. It makes it out of balance. It makes it harder to steady itself, if you will. So sometimes copper does something weird. Instead of ending with 4s2, 3d9, sometimes one of these, and it looks like a farther distance, and it doesn't really travel. One of the s orbitals goes up here, and it becomes 4s1, 3d10. If you have all of those 5 filled evenly, it's more stable, okay? And so what's that have to do with anything? Well, it turns out the S and P electrons are the ones that get gained or lost. And sometimes copper will form +1 ion and lose 1 electron. Sometimes it will form +2 ion. So here's all this underlying stuff. This is how it should be written. But sometimes, depending on what it binds with, you don't have any knowledge. There's no way to predict it, okay? So don't worry about that. I'm just giving you some information. Sometimes the D's are full and it only loses this. Sometimes it leaves it half full and it loses both. It depends on what it binds with, and you don't have a way to know that, okay? You just have to know that it can do that. So looking at our filling diagram, if the S2 is filled, that's great. That's how it's supposed to be based on the rules we learned. But some of the compounds that it forms, it looks more like this. Okay? And so it'll lose this 1 4s electron, if you will, and have filled 3d. Sometimes it will lose 2 from the 4s and still have a half filled 3d. Not a big deal. I just want you to see this now. This will be super critical for when we get to ions in chapter 7. Okay? Again, it's nothing you can predict. It's nothing that you can memorize. You just need to be aware that it can do that. All right, questions. I'm sure there's a zillion of them. Or are you just all asleep? You're probably all asleep. Never mind. If you think of a question, ask the, oops, not again. Oh, not again. Oh, beautiful. All right. So I'm going to show you what you're doing for me. So when you go into our classroom, classwork, you can open up a separate window or split your screen or whatever you do to watch me and do stuff. That would be good. Click on the noble gas configuration thing for me. I'm going to give you 3 elements. So the top of this is the slide that we had before with the periodic table and the blocks. I'm going to give you 3 elements. There's a last slide. Don't worry about it. I didn't. I had thought we would get more done. So I'm going to show you an example, and you're going to do 2. And I'm going to go fast because we're almost out of time. So please, on slide 2, type in boron. Or you can just jot this down on a piece of paper and come back to it when you do it, okay? So boron is element 5. It's right next door to carbon. This is really blurry. I don't know why. but you can look down another periodic table as well. It's right next door to carbon, which is element 6. So here's boron. So notice it's on the 1, 2, second row, and it's in the P block. So I'm going to go back here. Boron's element, atomic, oh heck. There we go. Its atomic number is 5. That means it has 5 protons. It also has 5 electrons, and all of those electrons need to live somewhere, okay? So, oh my goodness, there we go. It's on the second energy level. It's in the P block. Its last electron is going to go to P, and then on the MacBook, it's command period. I think it's control period on your Chromebooks. I'm not positive. Command period. 1. Because it's in the first column of the P block. So everybody here is P1, everybody here is P2, everybody here is P3, P4, P5, P6, except for P1. Okay. The next thing you're going to do is do a filling diagram. So 5 electrons all need to live somewhere. Those 5 electrons start with the lowest energy first. There won't be any exception stuff on your diagrams, okay? So 1s2, 2s2. That gets us to 4 electrons, and then we just need 1 more. 2, 4, 5. Configuration for boron, 1s, command. You have to undo it to get back into regular font. 2s, 2, and period, 2, B, 1. Right. And then the last thing is what noble gas configuration is it going to be? We'll go back here. What's the noble gas before row 2? It's helium. So you're going to put square bracket, capital He, close bracket, and what's different about boron from helium to S2 to P1? Helium plus 2 plus 1 gives us boron. So look at that again. All right, so the 2 elements that this class period is doing are phosphorus and calcium, and I'll type them into the chat. You're going to do the configuration for calcium, same process, moving all these over here, figure out what atomic number, what protons, what electrons. Okay. And then you're going to do the configuration, and then you're going to do the noble gas configuration. Same for phosphorus. Phosphorus is on slide 3, calcium is on slide 4. There is no slide 5, you can just delete it. Questions I can answer. I'd be happy to stay after. Anything I can help you with. I'm going to stop recording.